Okay, so as I said, the percentage or the amount of the loss depends on the airflow pattern, right? So typically, if you have, let me write it down. So this can vary from significantly from, so this drift loss can vary from 0.01 to almost like 1%, right? So typically it is, this D is 0.3 to almost 1% for natural draft towers, right? Whereas this is slightly less. So this is around 0.1 to 0.3% in, this mechanical draft towers. So mechanical draft towers can be again of two types. One is force type, one is induced type, right? And this is typically 0.01% if the cooling tower has drift eliminators. So what are these drift eliminators? These drift eliminators are sort of, I would say, sort of loops that is present close to the, the air exit, and due to the strong velocity of the air towards the exit, as it hits these loops, the water gets separated out and it gets mixed to the recirculation water. So this is typically known as the drift eliminators. A common example of a drift eliminator would be to look into, what shall I call? Yeah, so if you recall, nowadays we don't see that much in the train. I mean, the non-AC coaches, where you have the normal, coaches, and there the window has two types of, shutters. One is the glass shutter, and one is that, that louvre type shutters, where you have this, this iron or the steel blades pointed downwards, right? And why that they are there? It is essentially to remove, or to, so that you can have the passage of the wind, but the water will not come into here. And mostly during, if it's very hot, you can use that one instead of the glass, because of that air will pass into it, whereas the sunshine, or there is this kind of shade that is there due to these loops, right? So these loops are typically sort of, you can think of them to be kind of the drift eliminators, right? So there is a sudden change in the direction on the impact of the air on those drift eliminators, and as a result, so generally they are also circular in type. So there is a strong, this centrifugal action which also takes place along these loops or these bend plates, and as a result, the water gets separated. Right, so there is a significant change in the velocity, and naturally the air and the water velocity will be different, and based on this you are able to separate it out. Right, so these are typically known as the drift eliminators. So if you use drift eliminators, the drift loss can be significantly reduced, but please note that these come up with an additional cost, right? So there is another thing that I want to talk about is bleeding or blow down. This is a very common, concept or idea that is very important in a cooling tower operation. Now, what is this blow down or this bleeding? I mean, can anyone make a random guess? What do you think is blow down or this bleeding means? This is an operation that we do on the cooling tower, and the question is what essentially this means. Anyone? Come on. I just wanted to make a guess, maybe an educated guess. Anyone? Siddhant? Bhavna?
Yes, sir.
So what do you think? Make a guess. Essentially this blow down.
Maybe it is related to reduction in the velocity.
Of what? Air or water?
Air.
Okay, not really. Anybody else? Yash, are you there?
Yes, sir, I'm here.
So what do you think blow down is?
Sir,
Just, I mean, if you are to make a guess.
sir, the small droplets which remain in the pipe after, like
After?
after the whole thing is passed, like some droplets.
Not really, not really. It is something to do with the water.
Okay.
Okay. Anybody else? Shubham? Shubham, are you there? Shomil? Ayush?
Sir, I just searched in the internet and it says that when water evaporates from the tower, dissolved solids remain in the recirculating water.
Mm-hmm. So what is blow down then? Or bleeding? That is true.
Yes, as
So,
more water evaporates, the concentration of dissolved solids increases. So if
right,
the concentration gets too high, then the solids can cause scale to form within the system.
right. So what is blow down? Whatever you have said is right. Can you think like what does blow down then means? You're almost there.
So like the cooling tower won't work if that happens.
Uh,
Stop working.
it's not that way. See, most what is the issue with the dissolved solid is that they scale and ultimately they foul the surface of the heat transfer equipments or mass transfer equipments, right? That is the problem with the dissolved solids with long period of use or even in the short term also because of this dissolved solids. And what are these dissolved solids? I mean, all of you know very well these dissolved solids are nothing but chlorides, carbonates, sulfates that are present in water, right? So these solids essentially starts to form the scale over the surface of these equipments. As a result, the additional layer on the surface, right? And that layer will have different, this heat transfer properties. Its thermal conductivity would be low, and this heat transfer would be significantly reduced, right, than its designed performance, isn't it? That is the problem with scaling, right? So it will, once it starts to form a scales, and as the scale layer grows, that the thickness grows, the resistance to the heat transfer will continuously increase, and as a result the net heat transfer will reduce, and possibly it will go out beyond, I mean it will reduce beyond whatever this design range is there, right? And then accordingly the the downstream or the upstream systems will also be affected, because if one of my unit does not deliver or does not perform what it is designed for, then I have put the other systems, or I have optimized the process parameters or operating conditions based on that only, right? So other things will change, and this scale will also affect the other equipments, right? So that is the reason this frequent cleaning has to be done to remove these scale surface. But if the scaling is excessive, then at some point of time it will degrade the equipments also, right? So these scales will also start to degrade, and after some time there will be huge, loss of the equipments. So cleaning to some extent does help in reducing the fouling or the scaling, but ultimately this will also reduce the lifetime of the equipments also, right? And in a continuous plant, whenever you want to do cleaning, you have to shut it down. So there is also an economic loss due to the stop. I mean, due to this, interruption in the productivity. So now, what is this blowdown essentially is that, as you have rightly said, that with time, as more and more water gets evaporated, they are drifted away, the concentration of the water will continue, I mean, concentration of these dissolved solids will continue to increase in this circulated water, right? Because this circulated water is continuously recycled. Right? It is not I will talk about the fresh water addition also. So this water is continuously recycled, right? And the water volume will also decrease because you are having losses due to evaporation and all. Right? So the water quantity will decrease, but you can still maintain the same kind of flow rate, right, in the circulation. Now, as continuously this water gets evaporated, the concentration, the dissolved solids won't evaporate, right? So that will make the concentration of these dissolved solids in the circulation water will continue to increase. Now, if it increases, when it increases beyond a threshold limit, that is decided by the manufacturers, that will cause significant amount of scaling or fouling, and then you have to stop it and all. When it starts to hit that range, then you cannot further operate it. So what is this blowdown? You bleed, or if you purge out an amount of the this concentrated liquid, just throw it out from the system, and that you use fresh water to make up the volume. The system also need a significant amount of the this volume of the water, right? That to after some time, to some extent it will manage if the water volume reduces, but after you make this bleeding, you have to compensate this lost water by some makeup water. So this bleeding or this blowdown is draining out some part of the concentrated circulated water. The water that is getting circulated, part of it has to be bled out or purged out, so that you have makeup water is the fresh water. You add fresh water to it, so that the concentration again is reduced, right? So after it becomes too concentrated, you have to bleed out, because you just cannot dilute it any further. Dilution, you can dilute it, but then again that will increase the volume too much, right? Let us say I have started with 100 milligrams per liter as my dissolved solids. After a few days of operation, I find that the concentration has increased to from 100 to, let us say, 300. Right? It can happen continuously due to this evaporation. A lot of evaporated water is already lost out, right? So that will increase the this TDS this dissolved salt concentration to 300 milligrams per liter. Now to again bring it back to 100, and the manufacturer said that you cannot exceed beyond 200. To again bring it down to, let us say, 150 or 200, I have to double the volume to bring it to 150, and doubling the entire circulated water may not be a feasible solution. Right? I have to add the same amount of fresh water. So what you generally do, you bead out, let us say, 20-30% of the water, and that you make up with the fresh water to reduce the concentration level instead of significantly increasing its volume by dilution. So you are essentially doing a dilution, right? But you are also reducing the volume and adding more makeup water, so that the net volume of the circulated water does not increase too much. Okay, so if this is what is blowdown. So blowdown or bleeding is purging out or taking out some fraction of the concentrated liquid that is circulated in the cooling tower. Now, eventually you can realize what do you mean by this makeup water. So this makeup water is the fresh water that is added to compensate for this loss. right? So let us say the makeup water, we call it as M. So what are the losses? One is the evaporation loss, one is the drift loss, and another is the loss due to blowdown or bleeding out. There could be some amount of loss due to some operational leakage and all, but for ideal system this leakage will not be there. So it is the summation of the evaporation loss, the drift loss, and the loss due to this blowdown or bleeding. Of course this blowdown amount is the highest among the all three, right? So this is what makes up, I mean, these constitute the makeup water that you need to add so that the volume of the water that is in circulation more or less stays the same, right? But still with blowdown after bleeding after some point of time, you will still find that you need to then make a shutdown to do the cleaning and to throw away the whatever the circulated water is there, and you again start with the fresh water. But this bleeding actually essentially helps you to delay this cycle or this maintenance schedule, and also you can have a continuous operation without this shutdown. So you can do a bleeding at least 3-4 times, right? But after some point of time you will see that it is further not possible to bleed out and add makeup water. So the concentration becomes so high, then you have to essentially stop. You have to take out all the water and to restart again with fresh water altogether. And in that process you can also do some cleaning of the this surfaces of the equipment over which some scales may have formed. So is this bleeding blowdown clear to everyone? This is a very common thing that you will find in the process industry. They will always talk about this blowdown, right? So I hope all of you are clear with this thing, this blowdown.
What is this plus L?
Say yes, please say.
Sir, what is this plus L?
L is the leakage. If there is some leakage in the system, that has to be also compensated with the makeup water, isn't it? There could be some leakage. That's what I'm saying. But in an ideal system, there will be no leakage. But practically, that is what we see, that there is also some amount of leakage that happens here and there in a plant. Right. So please note that this fresh water, I mean, this is where I feel always, this actual plant visit could be helpful. The fresh water comes from a nearby river or nearby lake or some underground resource. So there is a significant amount of pipelining and, all these pump houses are there. Then it goes into the big cooling tower units, and this water gets continuously recycled. So there is a makeup water line, there is a recycling line, there is this blowdown and bleeding line. So there is a lot of piping network that is there in the cooling tower. So because of all of this, and this cooling tower is also quite large. Generally the cooling water typically the flow rates starts from 100 meter cubes per hour to 500 meter cubes per hour, right? 1 meter cube is equivalent to 1000 liters. So you can really understand the scale of the water that goes into this process, and that is per hour. If you make it over 24 hours, you can really imagine the amount of water that is handled in this in this kind of cooling water plants. Okay, so there could be some possibilities of some leakage somewhere. That has to be again compensated by the makeup water. Right? But in ideal situation, there is no leakage, so you can drop that leakage term. This is clear to all of you?
Sir, could you please just go to slide number 4 for once?
Okay.
Yes, sir. Thank you, sir.
Right, so there we talked about evaporation loss, and the first one I said about the heuristic formula. It's 6-degree drop, around 0.8 to 0.9% of the water is lost. Then there is this empirical formula from the Perry's handbook. You can also do a heat balance, right? You can also do you can work out the change in the humidity, and from there also you can find out how much of the water that has gone into the circulated air.
Sir,
Yes.
can you please repeat what was the name of that law, that 6-degree drop in the
There is no law. That is just a thumb rule that with experience, with time over the that engineers have came into a quick calculation if you want to make. It's just a thumb rule. but there is no, I mean, there is no scientific basis behind it. It's just a thumb rule based on field observations, right? From process engineers, slowly this is how the information has got, collated, and people have realized that, for every 6-degree drop, approximately you see around 0.8 to 0.9% of the water is lost. And then there is also an empirical formula where some more calculations has been, or observations, making some observations, you could also have this kind of empirical formula, which is slightly more accurate. Okay. Let us proceed from here. There is something known as the holding capacity. Of the cooling tower. So what is this holding capacity? This, I mean, you can easily understand or interpret from the name itself, that is the amount of water that is held up in the, in the cooling tower, and this is typically is in meter cubes or cubic meters. So this is the amount of water that is hold up, or this is the amount of water, I should say, the capacity of the cooling tower in some way. This amount of, this is a hold up volume in the cooling tower. Okay, so that is known as the holding capacity. Then there is something known as the holding time index. Known as the HTI. So what is this holding time index? So this tells you that it is the time required to reduce the, to reduce the makeup water, or to reduce the chemical or the makeup water added to the system to 50% of its original concentration. Right, so you can think of this to be some sort of the half-life of those dissolved solids in the system. And how this is estimated? It is estimated based on the, I mean, I should not say assumption, but based on the idea that the rate of decrease of the concentration of these dissolved salts at any instant of time is proportional to its concentration. I will repeat it once again. So this half-life index, or the holding time index, is essentially a value that tells you that what is the time needed to reduce the concentration of the dissolved solids to half of its concentration, half of its original concentration. So you can think of this to be the sort of the half-life of the dissolved solids in the system, and this is estimated based on the assumption or the idea that the rate of decrease of concentration of these dissolved solids at any point of time is proportional to its concentration. So typically this holding time, HTI, is represented as like this. And how the concentration will reduce is by the use of makeup water. Okay, and again, the volume of the makeup water depends on how much of the loss that you are having due to the this what should I say, the bleeding, due to the drift, and due to the evaporation. Sorry, so this should also be the evaporation. So this is essentially the makeup water volume. Right, so this HTI, typically why this is important, because this HTI gives you an idea about I mean, normally what you use, there are some very proprietary chemicals which is added to this cooling water line to reduce the scaling of these dissolved solids, right? And there is these chemicals are like quite expensive, and they are very secret. And most companies do not even know what chemicals they're using, because that has been procured from some licensor. So these are very proprietary chemicals, and these are generally provided by the people who actually built the cooling towers, and this determines that how much of the this dissolved solid concentration you can handle in your system, right? It's not essentially the fouling, but it is also the efficacy of the chemical treatment program or the chemical treatment technology that you are having to reduce the effect of fouling due to these dissolved solids, right? So that is the reason. So these are some kind of, so this fouling can be chemical fouling, they can be biofoulings, and also these chemicals also make sure that you add some kind of biocides or some kind of, it's a mixture of different chemicals actually, which reduce the fouling behavior of these dissolved solids, right? So essentially this half-life, so if you want to so one would essentially want the half-life to be as high as possible, right? So and that depends on the, as I said, on the chemical treatment program or chemical treatment technology that you are using in your system or in your plant, so that this holding time can be improved, and accordingly the maintenance schedule and its makeup, water circulation rate, etc. are decided, right? The cycles are all fixed based on this how efficient these chemicals are. So this is also one thing I should enlighten all of you, that with I mean initially when these cooling waters are there for last 50-60 years, right? But this use of these proprietary chemicals to reduce the fouling has only been in place over the last 20-25 years. Before that there were some very local chemicals are there, or just you want to add some kind of very common this kind of water treatment things, like for example this what you call alums, and also has to precipitate these dissolved solids and all, right? But nowadays these are like very proprietary chemicals, and if you look into the websites of these Dow chemicals, or this also you have this Honeywell, these are the companies who prepare these sort of proprietary chemicals, so that and they are of particular dose. So if you add them, this fouling tendency of these dissolved solids typically reduce significantly. So you can, what essentially it means, you can continue to operate, or this allowable limit of the dissolved solids in your circulated water can be enhanced, right? Because of this dosing of the treatment chemicals. And essentially you can have this this continuous operation for a longer time without the need of shutting it down and again restarting with fresh water. So that time can be increased, and of course, as you know, the less if the frequency of these cleaning or this halting of the cooling water is reduced, you will have more productivity. As simple as that, right? So that is how it is linked. So typically for, okay, so with this now let us I want to proceed to the thermal design of the cooling tower. So far we have been discussing about several types of cooling tower, its internal classifications, different phenomena that takes place, what are the different things that you should know about the cooling tower as a process engineer. Now we have to move towards as a designer, and how do you design or sizing of the cooling tower. So essentially by designer sizing or the process design, we means that what should be the the diameter, what should be the height of the cooling towers, right? So these designs are based, there is this international standards are there. So this industrial cooling tower standards STD 203, this is the particular codes, like how you have the IS codes, how you have the this ASME codes when you have designed for the heat exchangers and all. Similarly, these sort of manufacturers association and engineering associations are there who prepare the standard codes. So for the design, this is the code that is generally followed. There is another code STD 202 which is used to follow for the testing, right? So these codes actually tells you that these are the things that you have to follow while designing. These are the protocols that you have to follow during testing. These are like the benchmark guidelines that is provided, and you have to follow them. So in our case, the process design, what we will do is based on this STD203. Okay, so let's talk about it. So as we start to make the design, and for any design or making any model calculations, always it is essential to think of the assumptions, because all designs, all calculations in the world are based on some sort of assumptions in some way. And slowly, the more assumptions that you relax, the more realistic the system becomes. But assumptions are very necessary to tell you about the limits of your calculation, to tell you like what is the range of validity or under what circumstances this particular calculation or this model or this theoretical derivation won't work. And also this is used to simplify your problem, isn't it? That's why assumptions is very, very essential before you start to make any process calculations. So the two assumptions we will make here, and it is very important in this case to simplify the problem essentially. So for the first assumption is that we will consider that this loss of this circulated water, right, is very less. Now, so far you must be, you must be thinking, so far we have been discussing about the loss of water and this, that, and all, but now suddenly while designing, we will assume this. So why? Is because what is this loss of the circulated water I am talking about? I am talking that the difference in the circulation rate in the inlet and the outlet of the cooling tower at any instant of time is very small. I'm not talking about over a time period of operation. I am talking about that at any instant of time, whatever is the cooling water flow rate that we are talking about, that is not changing much, between inlet and outlet. It is of course changing a little bit. Otherwise, how with a period of time it will change, right? But we are talking about that this change is very minimal because we are compensating with the makeup water. That is one thing. And second thing is that between the inlet and the outlet, at any, so whatever is the time or this, so this water stays in the cooling tower is not long. That's why the loss to evaporation and drift may not be that significant. So this is one assumption we are bringing into the picture. So we are considering that the water or the liquid flow rate is constant, right, in this tower. I hope this is clear to everyone. The second assumption, we are saying it is adiabatic cooling. So of course, in an ideal situation, this is what we want to achieve, that the drop in the water temperature is only due to the loss of heat by evaporation, right? But it may not be that case in the reality. That may be some sort of heat exchange with the surroundings also, right? But that we are ignoring. So this is like, you can think of that this is more or less a realistic approximation, that we are considering that there is no heat exchange through the walls of the cooling tower, right? And the previous one, the loss of the circulated water is very less or insignificant. That is sort of an assumption we made to simplify our problem. And partially that is also taking into the engineering assumptions that we try to have this makeup water so that the water flow rate remains almost constant. So the makeup water is continuously monitored and controlled. Right? It cannot stay the same because continuously there is some loss due to evaporation will be there. And if you're continuously bleeding out something, then you have to continuously have the makeup water supplied. And these rates can change depending on whether you are having a natural draft, induced draft, or the rate of production can also be different at different times of the day and night. Seasonal variations could be there. This evaporation could be less in the winter, in the rainy season, it would be more in the summer and the winter. So accordingly, makeup water needs to be controlled. Right, but with appropriate choice of process this control systems, we can think of this, that the makeup water is more or less accurately controlled or balanced such that the circulation water velocity remains, the circulation water flow rate remains more or less constant, right? And in between the inlet and the outlet, there you are having loss due to evaporation, and that we are considering that it is very insignificant, right? But you can also work that out considering, I mean, without this assumption also, but that will make it complex. So the first start, let us consider that this loss of water is very small. So how do you work out? So it's all about, enthalpy balance, mass balance, and heat transfer only. So if you think of a cooling tower, I will just introduce you here, and will of course work out in the next class in detail. Let us say this is my cooling tower. You are having, this is air inlet, right? And this is air outlet. And here you are having water inlet. And here you are having water out. Let us designate the air inlet conditions as Tg1. You know what is Tg, that is the gas temperature at the inlet. Then let us say the humidity is Y1. Enthalpy, let us say as H1. I am putting a prime because these are all in mass units. And the air velocity, let us say I call this as GS, right? Similarly, for the water inlet, I will say that the water flow rate is L1. Water temperature, I will say like TL2. I am just marking the bottom as 1 and the top as 2, right? So please follow this nomenclature. And of course, the enthalpy is HL2, right? So here at the bottom, the flow rate would be same, that would be L. I will write this as TL1. I will write this as HL1, right? For the gas outlet, flow rate would remain the same, right? I will mark it as Y2 prime, H2 prime, and Tg2. So now let us say I want to make a small, differential balance. You consider this is how you normally do, isn't it? You take a small cross section of delta Z, right? So if I try to make a heat balance, right? If I try to make a heat balance across this region, so I should mark it as red. So this would be like L, and this would be like L plus DL. Sorry. Liquid flow rates are not changing. Right. So across this small cross section, what is changing? It is the temperature of the water, and it is the enthalpy of the air that is essentially changing, isn't it? That is how you are going to make the net heat balance. So the loss in heat by the water is equal to the gain in heat by the air. So how you are going to estimate the heat that is gained by the air is by the change in its enthalpy. And how you are going to estimate the loss of the heat in the water is by calculating its drop in temperature. Isn't that is one way of doing it? So this temperature, this of course the air temperature would also change, right? Enthalpy changes means air temperature will also change. But the easiest way to account for is to write down down this enthalpy balance based on the change in the temperature of the liquid and the change in the enthalpy of the gas. We'll also talk about change in the temperature of the air is also something we'll talk about. Not worry about that. Right? So, and also the enthalpy of the liquid will also change. So everything will change, right? As far as the heat transfer characteristics are concerned. So as the liquid temperature also changes, the liquid enthalpy will also change. Similarly, as the gas enthalpy changes, the gas temperature will also change. So what are the things that will change across this small cross section? It is the temperature of the, air and the water, and also the enthalpy values of the air and the water. So if I want to make a heat balance, as I was trying to say, across this small section, so, or let us say I want to make an enthalpy balance across del Z. So the enthalpy, the inlet, and let us say if I want to, calculate out the change in the water temperature, what I will write, or the enthalpy change in the water can be equated to the drop in the temperature, isn't it? So the enthalpy change, this across delta Z, so let us say HL and minus HL similarly, so entire thing would be multiplied with L, and here also GS. So the change would be H. Let us write it as G instead of 1 and 2. Isn't it? Something like this. So what do you get? L DHL is equal to GS DHG prime. Now how you can write this HL? So L into, you just multiply with the specific heat of water and with the change in temperature. So this is what we can write down, but here it is not so straightforward. So let us write it as GS and DHG prime. In the case of the gas, you just cannot multiply with the heat capacity to the heat capacity to the change in the temperature. Is this clear to everyone? We will also talk about details about the change in the enthalpy on the gas side also. That is also something you can also write in terms of the temperature change, but at least this equation is clear to everyone. So one interesting thing, or this quick observation or interpretation that you can bring it, that if you make the enthalpy balance across this whole tower, right, across this whole tower, if I try to make the enthalpy balance, what do I get? I can easily write LCWL, the change in the temperature. So TL2, the inlet temperature is higher than the outlet temperature, right, for the case of the water. So this is the amount of heat that is lost by the water, and the amount of heat that is gained by the air is H. So the air enthalpy would be more at the outlet than the inlet, is it? So this is the balance that I can also write for the entire tower. Is it or is it not? So we'll stop here today, and again we will take it up from here in the next class. So any questions from anyone so far, guys? No? Yes? Okay then, so if there are no questions, we stop here for today. And again, we'll meet on this Friday to continue from here. Thank you, everyone.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.